Hello students, this is Nikhilian, Assistant Professor, Department of Civil Engineering, IIT, Mangaluru. In my previous session, I was discussing about shear stress calculation of a prestressed concrete member, and I had also discussed about some numericals. Also, in my previous session, I had discussed about different modes of shear failure. And now in this session, I'm going to discuss about few numericals based on shear failure of a prestressed concrete member. So let us consider a few examples based on web shear crack failure and flexural shear crack failure. So let us consider a first example. The cross section of a bridge girder is made up of T section with the following details. Top flange width and thickness is 600 mm and 230 mm. Thickness of the web is 150 mm. Distance of centroidal axis from the top of the section is 545 mm. Area of cross section is 3,28,500 mm square, and second moment of area is 665 into 10 to the power of 8 mm to the power 4. The girder is used over an effective span of 25 meter. The tendons with cross section of 2300 millimeter square are parabolic with an eccentricity of 650 mm at the center of span and 285 mm at the support section. The effective pre-stress in the tendon is 900 Newton per mm square after all losses. If the tensile strength of concrete is 1.6 Newton per mm square, estimate the ultimate shear resistance of the support section and the maximum permissible uniformly distributed working load on the beam using an overall load factor of 2. So here in this question, they have not mentioned whether we have to calculate the ultimate resistance of a member under web shear crack or flexural shear crack, but they have given to estimate the ultimate shear resistance of the support section. So support section means you should always remember that at the support section the failure is due to web shear crack failure. At the support, the failure is always web shear crack failure. Therefore, we should consider the first condition. So let us see the cross section and details of a given member. So here it is a cross section of a member. So it is given that the girder is a T section which is having the width of flange is 600 mm and thickness of the flange or depth of the flange is 230 mm, and it is also given that from the top edge of a member the centroidal axis lies at a distance of 545 millimeter. So from the top the centroidal axis is 545 millimeter and thickness of the web is 150 millimeter, and this is the longitudinal view. The span of a girder is 25 meter. The cable is parabolic cable, and the eccentricity of a cable at midspan is 650 millimeter, and at the supports the eccentricity is 285 millimeter. So at the support it is 285 and at the midspan it is 650 millimeter. So as I told you, we should consider web shear crack condition because it is given to calculate the ultimate shear resistance of the support section. So at the support section always it is web shear crack failure. So to calculate the shear resistance due to web crack is equal to VCW is equal to BW into I by S square root of FT square plus FCP into FT plus neta P sin theta. So as I told you in the previous session, to calculate the ultimate resistance due to shear, we have two equations. So the shear resistance can be calculated using this equation, or else we can also consider 0.67 d instead of this I by S. So let us consider this formula. So we should select the formula as per the given data in the question. So first, moment area is obtained as S is equal to A into Y bar. So this is the formula. We know what is width of a web, it is given, it is 150. We know what is I, we can calculate, or it will be given in the question. So S is equal to A into Y bar. So A into Y bar means, always remember that we will calculate shear force or shear resistance with respect to the centroidal axis. So when we calculate the shear resistance or shear stress with respect to the centroidal axis, we should consider the area above the centroidal axis or below the centroidal axis depending upon the asked condition. So here it is required to calculate the shear resistance with respect to the centroidal axis. Hence I will consider the area which is above the centroidal axis. I am going to consider this area, this portion of the web and this flange. So I should calculate A into Y bar for this portion, for this flange and this web. You see here, area of the flange is 600 into 230. So 600 is the width and 230 is the thickness, that is the area of the flange. And 430 is the centroidal distance of this flange with respect to the centroidal axis. So from here to here it is 545 millimeter from central axis to the top edge of the member. And to calculate y bar of this section, we should consider 545 minus 230 minus 230 by 2, right? The centroidal axis of the flange section with respect to the centroidal axis of the whole section is equal to 545 minus 230 by 2, that will be 430. So this is A into Y bar of flanged section, plus now considering this portion of the web, so the thickness of the web is 150. So 150 into 315. 315 is the depth of the web. From here to here it is 545 millimeter. The thickness of the flange is 230 millimeter. Then the remaining height of the web is 315 millimeter. So 150 is the thickness of the web and 315 is the depth of web, which is the cross section area of the web, into then centroidal distance of the web with respect to the centroidal axis of the section, that will be equal to 315 divided by 2, that is 157.5. So this is 315 divided by 2, which is 157.5. So S is equal to 665 into 10 to the power 5 millimeter square. So I by S, so this term I am calculating moment of inertia by second moment of inertia. I by S is equal to 665 into 10 to the power of 8 divided by 665 into 10 to the power of 5. So this we have calculated, and moment of inertia is given in the question. Second moment of inertia is 665 into 10 to the power of 8. So I by S is equal to 1000. Therefore FCP, so here FCP is nothing but it is the compressive stresses with respect to centroidal axis of the section. So we can also call FCP as Fx. So FCP is equal to P by A. So I said you FCP can also be written as F into Ex. So Fx is the compressive stress at CE, centroidal axis of the section. So that is P by A. So in the question, pre-stressing force P is not given. So they have given the cross-section area of the cables and what is the effective pre-stress in the cable. So see here, it is given that the tendon with a cross-section of 2300 mm square and the effective pre-stress in the tendon is 900 Newton per mm square. So using area and stress of a cable, we can calculate what is the pre-stressing force induced or applied onto the cable. So 2300 area into 900 stress divided by area. So total area of the cross section is given. So total area of the cross section is 3,28,500 millimeter square. So substituting that, we will get compressive stresses in the section with respect to the centroidal axis FCP or Fx is equal to 6.3 Newton per mm square. Then in the formula we calculated what is this, we know what is width of the web, and we calculated what is FCP, and we should calculate what is neta P. So neta is the loss ratio, but in the question the loss ratio is not given. Hence, we shall consider neta as 0. That is, there is no loss in the section. Therefore, P is equal to area into stress, 2300 into 900. Therefore, P is equal to, that is, pre-stressing force is equal to 207 into 10 to the power of 4 Newton. So the given cable is a parabolic cable. So to calculate the slope, theta is equal to 4E by L, or alpha is equal to 4E by L. So E is the dip of a cable. So here we have two eccentricities. So in this condition, to calculate the effective eccentricity, we should consider the distance between the edges and the midpoint. So with respect to the end points of a cable and with respect to the center of a cable, the dip is 650 minus 285. 650 is the overall depth or overall eccentricity of the cable at the midpoint, and 285 is the eccentricity of the cable at the supports. Therefore, the net eccentricity will be this much. So, the net eccentricity will be measured from the edges of the cable. So, from this will be the net eccentricity. So, from here to here, it is 650 minus 285. That will be the net eccentricity. So, 4 into 650 minus 285 divided by L. So L is a span of a beam, and span of a beam is given, it is 25 meters. So converting 25 meters into millimeters, it will be 25 into 10 to the 25 into 10 to the power of 3. Therefore theta is equal to 0.0585. So we calculated this ratio, that is I by S. We calculated FCP, we calculated what is neta P, and also we have calculated what is theta. And FT, tensile stresses in the member, is given in the question. See here, the tensile stress or tensile strength of the concrete is 1.6 Newton per mm square. So now we know all the values of this formula. So substitute the values in the given formula. So before that there is one more substitution, neta P into sine theta. So neta P into sine theta, which is equal to 207 into 10 to the power of 4, that is neta P, and sine theta is 0.585. So the slope is very small, and sine theta will become theta. So 207 into 10 to the power of 4 into 0.585, which is equal to 122 into 10 to the power of 3 Newton. Therefore, VCW, ultimate shear resistance of a member at the support section is equal to 150 into 1000 square root of 1.6 square plus 6.3 into 1.6 plus 122 into 10 to the power of 3, which is equal to 655 kilonewton. So the member can take up a shear force of 655 kilonewton at the support. And here you please note that this we can also write as minus 1.6 because it is a tensile strength or a tensile stress. So in a prestressed concrete member, tensile strength or a tensile stress is considered as negative. Therefore, this we can also consider as minus 1.6. So even though it is minus 1.6, it is 1.6 square, it will become plus. So the maximum shear force is 655 kilonewton. We need to calculate the UDL that a member can safely take with the load factor of 2. So to calculate that, first I will calculate what is the shear force under working load with the load factor of 2. So the maximum shear force under working load 655 by 2. So 2 is the load factor. So that will be 327.5 kilonewton. If Q is uniformly distributed working load over a span of 25 meters, so we know the shear force in a support is 327.5 kilonewton. Then we can calculate the UDL that can be permitted on a beam, that is Q into 25 by 2, which is equal to 327.5. Therefore, Q is equal to 26.2 kilonewton per meter. So this is WL by 2. So the relation or the formula to calculate shear force for a simply supported beam which is subjected to UDL is WL by 2. So W is taken as Q here, and here the Q is a load which is unknown and W is the span by 2. That is equal to the shear force is known, it is 327.5 kilonewton. So Q is equal to 26.2 kilonewton meter. So a beam can safely carry a working load of 26.2 kilonewton per meter. Now let us consider one more example. The cross section of prestressed concrete beam is an unsymmetrical T section with an overall depth of 1300 mm. Thickness of web is 150 mm. Distance of top and bottom fibers from the centroid are 545 mm and 755 mm respectively. At a particular section, the beam is subjected to an ultimate moment. M is 2130 kilonewton meter and shear force is 237 kilonewton. Effective depth is 1100 mm. Cube strength of a concrete is 45 Newton per millimeter square. Effective pre-stress at the extreme tensile phase of the beam, that is FCP, is equal to 19.3 Newton per mm square. Second moment of area, that is I, is 665 into 10 to the power of 8 millimeter to the power 4. Area of steel in section AP is 2310 millimeter square. Tensile strength of tendons, that is FP, is 1500 Newton per millimeter square. Effective stress in tendons after all losses, that is FPE, is equal to 890 Newton per millimeter square. Estimate the flexural shear resistance of the section. So when we analyzed the previous example, it was a web shear crack because it was asked us to calculate the ultimate shear resistance at the support section. So support section means it is always a web shear crack condition, but here it is directly given to estimate the flexural shear resistance of the section. So that means we are calculating for the second condition. So the formula is given here. VCF is equal to 1 minus 0.55 FPE by PE tau C BWD plus M naught by M into V. So all the datas are given in the question. So it is a unsymmetrical T section with the overall depth of 1300 millimeter and thickness of a web is 150 mm and distance of a centroidal axis with respect to top and bottom fibers are given, moment is given, shear force of a section is given, effective depth is given, that is 1100 millimeter, then cube strength of a concrete is given, tensile phase of the beam, pre-stress at the extreme tensile phase of the beam is given, I is given, area of steel is given, tensile strength of tendon is given, and effective stress in the tendon after all losses is given. So by considering all these data, we should calculate the flexural shear resistance of a section. So for this problem, we need the codebook IS 1343. So this formula is also available in codebook IS 1343 in page number 46. So here FPE is given in the question, FP is given, BW is given, that is width of the web, D is given, this is a small d. So small d means it is effective depth. Effective depth is given, that is 1100 mm. M naught is not given, M is given. M is ultimate moment 2130 kilonewton meter and V is given. Shear force is equal to 237 kilonewton is given. So in this formula we need to determine what is tau C and what is M naught. So to calculate M naught we have the formula 0.8 FEP into I divided by YB. So 0.8 FEP is 19.3 into 665 into 10 to the power of 8. This is moment of inertia divided by 755. So substituting all these values, we will get M naught is equal to 136 into 10 to the power of 7 Newton millimeter. So here you should remember what is YB and what is FEP, because in your examination sometimes they will give effective pre-stress at extreme tensile phase of the beam. That's all. So or sometimes they will mention FCP. So suppose if they won't give this as FCP, then you should know effective pre-stress at extreme tensile phase of the beam means it is FCP, and YB means it is the distance from the centroidal axis to the bottom fiber of the section. Therefore, M naught is 136 into 10 to the power of 7 Newton millimeter. And we have one more term which is unknown, that is tau C. So to calculate tau C, we need IS 1343. In IS 1343 1980 in table number 8.1, we have design shear strength of concrete tau C. So tau C can be calculated using this ratio. So substitute the values of AP and BD in this formula. So 100 AP by BW into D, which is equal to 100 AP is area of pre-stressing steel, it is 2310 given in the question, and BW is 150 and D is 1100. And remember this, in the second condition when we calculate the ultimate resistance due to shear, that is under the condition of flexural shear crack, B is always BW. We will consider B as width of a web. So this from this ratio we will get 1.4. So see in this column we have different grades of concrete M30, M35, M40 and above. So here in the question, what's the grade of concrete given? It is M45. So for M45 grade and for 1.4 value in this column it is 1.4. This ratio is 1.4. So here we have 1.25, 1.5. So for 1.25 it is 0.74. For 1.5 it is 0.79. So you should see under this column because the grade of concrete is M45. So for the concrete grade more than M40 we should refer this column. For M35 this column and M30 this column. So by interpolating between 1.25 and 1.5 and between 0.74 and 0.79 the value of tau c is equal to 0.77 Newton per millimeter square. So substitute the values of m0 and tau in the formula. So the flexural shear resistance of the section is this equation. Substitute the formulas in this equation. So VCF is equal to, substituting all the values, the final value is 240 kilonewton. That is, a beam can take a shear force up to 240 kilonewton before it undergoes flexural shear crack. So in the question it is given that the actual shear force acting in the member is 237, but a member can take up a shear force up to 240 kilonewton before it undergoes flexural shear cracking or flexural shear failure. Hence, there is no requirement for the shear reinforcement. It is sufficient if we provide only minimum shear reinforcement. So next is methods of shear resistance in PSC member. So how the shear can be resisted in a prestressed concrete member. In general, there are three ways of improving the shear resistance of structural concrete member by prestressing technique. First one is horizontal or axial prestressing, prestressing by inclined or sloping cables, and third one is vertical or transverse prestressing. So by using these three techniques, we can resist the development of shear force, or we can make the section to be strong against the shear force. So design of shear reinforcement. So design of shear reinforcement is given in class 22.4.3.2 in page number 48 of IS 1343. So why we need to know about shear reinforcement? So see here we got the maximum shear capacity of a member is 240 kilonewton, but the actual shear force acting on the member is 237 kilonewton. Hence, in this case, there is no necessity of providing reinforcement, that is shear reinforcement. Suppose if the actual shear acting on the member is 300 kilonewton and the ultimate shear capacity of the member is 240 kilonewton. So, in such cases, we need to provide the shear reinforcement to resist the shear force. Hence, we need to know about shear reinforcement. So, shear reinforcement is given in this class 22.4.3.2 in page number 48 in IS 1343 1980. So, to calculate or for the design of shear reinforcement, the formulas are same as what we have used in the previous problems. Here you need to remember only these equations, that is for spacing of the cables, this equation and this equation. So these equations are given in the code book. So it is sufficient if you remember the clause and page number. So for design of shear force we have SV equal to ASV into 0.87F5 divided by 0.4B, where SCV or SV is spacing of stirrups along the length of a member, ASV is total cross section area of stirrup, less effective in shear. B is width or breadth of a member, which for T, I and L beams should be taken as the width of the rib, that is BW. Fy is the characteristic strength of stirrup reinforcement, which shall not be taken greater than 450 Newton per mm square. If the shear force V is less than 0.5 Vc and in the member of minor importance, shear reinforcement need not be provided. So there is a condition for the provision of shear reinforcement. If shear force is less than 0.5 V, then there is no necessity of providing shear reinforcement if the members are minor importance. When V exceeds Vc, shear reinforcement is required, and the shear reinforcement should conform to the relation SV equal to ASV into 0.87 Fy dt divided by V minus Vc, where dt is depth from the extreme compressive fiber either to the longitudinal bars or to the centroid of the tendons, whichever is greater. So these are the two formulas which is used for the design of shear reinforcement. So this is the formula which is used when V is less than 0.5 Vc, and this is the formula it is used when V is more than Vc. So let us consider an example. The support section of PSC beam 100 mm wide and 250 mm deep is required to support an ultimate shear force of 60 kN. The compressive pre-stress at centroidal axis is 5 Newton per mm square. The characteristic cubic strength of concrete is 40 Newton per mm square. The cover to the tension reinforcement is 50 mm. The characteristic tensile strength of steel stirrup is 250 Newton per mm square. Design suitable reinforcement at the section using IS 1343 recommendations. So here it is a pre-stressed concrete beam. It is a rectangular section whose width is 100 mm and depth is 250 mm. So here the beam is subjected for a ultimate shear force of 60 kN, and the compressive pre-stress at centroidal axis is 5 Newton per mm square. So at the centroidal axis, the compressive pre-stress is 5 Newton per mm square. That means FCP is 5 Newton per mm square, and the concrete grade is M40, and the cover thickness or cover depth is 50 mm. It is given that the steel stirrup is having a tensile strength of 250 Newton per mm square, and for this condition we should design a shear reinforcement using IS 1343. So first let us consider the given data. So B or BW is 100 mm, H that is depth is 250 mm, small d that is overall depth, small d that is effective depth, H is overall depth and small d is effective depth. So overall depth is 250 mm, and out of that 250 millimeter there is a cover of 50 millimeter. Therefore effective depth is equal to 250 minus 50, that is 200 millimeter. So shear force is given, that is P is 60 kilonewton. FCP means it is compressive pre-stress at the centroidal axis of the section. It is 5 Newton per mm square. FCK grade of concrete is given, it is 40 Newton per mm square. Fy is 250 Newton per mm square. So here again we have two equations to determine the shear capacity of a member. So two equations are, first one is web shear crack condition and second one is flexural shear crack condition. But here we should consider web shear crack condition because the shear force will be maximum at the support section, and at the support section the web cracks the cracks are developed due to web shear failure. Therefore, we shall consider the equation Vc is equal to Vcw is equal to 0.67 BWH into square root of Ft square plus 0.8 FCP Ft. So the formula is same. So Ft is 0.24 into square root of Fck, which is 0.24. Fck is given 0.24 into square root of 40. Therefore, Ft is equal to 1.517 Newton per mm square. Vc is equal to 0.67 into 100 into 250 into square root of 1.17 square plus 0.8 into 5 into 1.517. So substituting the values which is given in the question in this formula. So B is given, H is given, Ft we have calculated, Fcp is given, that is 5 Newton per mm square, and Ft. So Vc is equal to 48.4 kilonewton. Vc is 48.4 kilonewton. That means it is showing that the maximum strength of the member is 48.4 kilonewton in shear. It can take up a maximum shear force of 48.4 kilonewton. But here it is given that the maximum shear force acting along the member is 60 kilonewton. So in this condition, shear force is required because the capacity of a member to carry shear force is less than the shear force acting on the member. Therefore, what is the shear that has to be balanced? That is, balanced shear is equal to V minus Vc. V is the actual shear acting on the member, that is 60, and Vc is the capacity of a member to carry shear force. So 60 minus 48.4, which is 11.6 kilonewton. So here we should design a shear reinforcement in order to take up a shear of 11.6 kilonewton. Let us use 6 mm diameter two-legged stirrups. So for 6 mm diameter two-legged stirrups, the spacing is obtained using the formula SV is equal to ASV into 0.87 F into D divided by V minus VC. So ASV is the area of stirrups. So it is two-legged stirrups, hence it is 2, and 28.2 is the area of one stirrup, that is pi d square by 4, which is equal to pi into 6 square by 4. You will get 28.2. So this 28.2 is pi into 6 square by 4, area of a stirrup. 0.87 into 250 into 200 divided by 11,600. So 11,600 is, here it is in terms of kilonewton, and here it is being converted into newton, and this small d is effective depth. 250 minus 50, overall depth minus cover thickness, we will get effective depth is equal to 200. Therefore spacing is equal to 211.5 millimeter. So from the codal provision, the maximum permissible spacing is 0.75 d, that is 0.75 to 200, that is equal to 150 millimeter. So the spacing of stirrups should not exceed 150 millimeter, but we have got the spacing of stirrups as 211.5 millimeter. Therefore, adopt 6 mm diameter two-legged stirrups at 150 mm center to center. So this is about shear reinforcement. Now let us see some of the questions which were asked in previous examination. A prestressed concrete beam having unsymmetrical I section as a fiber stress distribution of 30 Newton per mm square, compression at top edge, linearly reducing to 0 at the bottom. The top flange is 2400 into 400 mm and bottom flange is 1200 into 900 mm respectively. The depth and thickness of web is 1000 by 600 mm. The total vertical service load shear in concrete at section is 2350 kN. Compute and compare principal stresses at centroidal axis and at the junction of web and flange below the centroidal axis. So this question was asked for 14 marks in semester examination. So here it is an unsymmetrical I section and the fiber stresses at top and bottom fiber of a section is given. That is FL1 and FL2 is given. So FL1 and FL2 means you remember the module 1 where you calculated FU1, FU2, FL1 and FL2. So here it is asked to calculate the stresses in the member, that is shear stresses in the member along the centroidal axis and at the junction of the web below the centroidal axis. So I should calculate the stress at this portion at the centroidal axis and also at this portion, that is at the junction of a flange and a web. So the details of a section is given. The top flange is having a width and depth of 2400 by 400 and depth and width of flange is 1000 by 600, and here the bottom flange is having width and depth is 1200 by 900. So the stresses at top fiber and bottom fiber is given. So here they have given the stresses with respect to working load condition, that is the given stress value is with respect to dead load plus live load, that means FL1 and FL2. So the top fiber stress FL1 is 30 Newton per mm square and bottom fiber stress FL2 is 0. So here I should calculate this and this value. So let us consider this as x1, so z1 and z2. So to calculate the stress at this junction and this junction, I need what is f of x at this point and what is f of x at this point. The stress at top fiber is 13, the stress at bottom fiber is 0. Then what is the stress at this point and what's the stress at this junction? So first we should calculate that stress and then we should calculate what is the principal stress developed in the section. So cross section area of a section is equal to 2400 by 400 plus 600 to 1000 plus 1200 into 900. So the cross section area is equal to 2.64 into 10 to the power of 6 millimeter square. To locate the position of centroidal axis, so here it is a unsymmetrical I section, hence we need to calculate what is the centroidal axis of a section. So to calculate the centroidal axis, y bar or y1 is equal to 2400 into 400. So area of this into centroidal distance of the top flange. So centroidal distance of this flange is 200 because I am calculating the centroidal distance with respect to the top fiber. So with respect to top fiber, the centroidal distance of this is 200. And for the next portion, 600 into 1000. So the thickness of web is 600 and depth is 1000. So 600 into 1000 into centroidal distance. So the centroidal distance of the web from the top flange is 900 millimeter. From here to here it is 400 and from here to here it is 500. So it is 900 plus area of the bottom flange 900 into 1200 and centroidal distance of the flange from the top fiber, that is 400 plus 1000 plus 450. So 1200 into 900 area, and centroidal distance of the bottom flange with respect to top fiber is equal to 1850 divided by area, which is 2.64 into 10 to the power of 6. Therefore y bar is equal to 1034.1 millimeter. So y bar is equal to 1034.1, that is measured from the top fiber from here to here, it is 1034.1. So centroidal axis is lying at that distance. Let us consider that as y1 and remaining bottom distance as y2. Therefore y2 is equal to 1265.9. So overall depth 400 plus 1000 plus 900. This overall depth minus this 1034.1 will use the remaining depth below the centroidal axis. So here in the question they have not given anything about the cable, whether the cable is parabolic cable or it is a straight cable. So let us assume the cable is a straight cable. So there is no necessity of this step. So we can skip these two steps. So effective shear force will be P is equal to V minus F sin alpha or V minus F alpha. So we have assumed the cable as a straight cable, therefore alpha will be 0, therefore effective shear force will be V. So V is given in the question, it is 2.35 into 10 to the power of 6. Here V is given here, it is 2350 kilonewton. It is given as vertical service load service in, it is given as vertical service load shear in concrete at the section is 2350 kilonewton, which is nothing but shear force. So in terms of Newton, it is 2.35 into 10 to the power of 6 Newton. And moment of inertia about centroidal axis of bending is calculated here. So BDQ by 12 for this section, BDQ by 12 plus A into A Rx square. So A is 2400 into 4 into Rx square. So Rx square means it is y bar minus y bar of the section. So y bar is total centroidal distance of the section and 200 is the centroidal distance of a particular section. It is 200. And coming for the web, the moment of inertia is BD cube by 12. B is 600 and D is 1000 by 12 plus area is 600 into 10 to the power 600 into 1000 into y bar minus y. Y bar of a whole section is 1334.1 minus centroidal distance of this web with respect to top fiber is 900 plus BD cube by 12 for bottom flange plus area for bottom flange is 1200 into 900 into 1034.1. This is the centroidal axis of a total section or whole section minus 1850 whole square. So 1850 is the centroidal distance of this flange bottom flange section with respect to the top fiber. Therefore I is equal to 1.533 into 10 to the power of 12 millimeter to the power 4. So next step, to evaluate principal tension at centroidal axis. So we know that the formula to calculate principal stress is equal to Fx plus Fy divided by 2 plus or minus 1 by 2 square root of Fx plus Fy whole square plus 4 tau v square. So here Fx is nothing but it is the stress in the horizontal plane, and Fy is the stress or pre-stress in the vertical plane. So here in this question, Fx is not given, that is the pre-stress component along horizontal plane is not given, but they have given the values of top fiber and bottom fiber. So by using these values, the by using the stress values at top fiber and bottom fiber, we can calculate what is the stress component at this centroidal axis and at the junction of web and the flange. So to calculate the principal tension, that is to calculate Fx for the centroidal axis. So to calculate principal tension along this axis, let us consider this stress diagram. So here from two similar triangles, from this triangle and this triangle, we can write as Z1 by 1265.9. So this is Z1 and this depth is 1265.9 is equal to 13. 13 is the stress at the top fiber divided by 2800, that is overall depth. So that is the overall depth of the section, this height of the stress diagram. We will get Z1, that is Fx at the centroidal axis is equal to 7.155 Newton per mm square. So shear stress at the centroidal axis tau is equal to P into A y bar divided by IB. So tau is equal to P is shear force, which is given in the question, 2.35 to 10 to the power of 6. A is cross section area of a section above the centroidal axis. So we are calculating the shear stress with respect to centroidal axis. Hence, we should consider the area which is above the centroidal axis. So consider the area which is being hatched here. So that area is 2400 into 400, and centroidal axis is 634.1 plus 200, and 600 into 634.1 is the area of the web which is being hatched, and 634.1 by 2 is the centroidal distance of the web portion with respect to the centroidal axis divided by I into B. I is moment of inertia, B is width of the web, which is 600 mm. Therefore, shear stress at centroidal axis is equal to 2.353 Newton per mm square. Therefore, principal tension at centroidal axis Fn2 or Fn is equal to Fx by 2 minus 1 by 2 square root of Fx square plus 4 tau square. So substituting the values, we will get Fn2 is equal to minus 0.7045 Newton per millimeter square. So this is the principal tension developed along the centroidal axis. Now to evaluate principal tension at the junction of web and the bottom flange, that is to evaluate the principal tension at this junction. So here at this junction, let us consider this as Z2, that is the stress in the member is Z2. So we know here it is 13 and here it is 0. By considering two similar triangles, this large triangle and this triangle. So here the base of the triangle is 13 and height of the triangle is 1300, 2300, and here the base of the triangle is Z2 and height of the triangle is 900 millimeter. So by considering similar triangles, Z2 by 900 is equal to 13 by 2300. Therefore, Fx or Z2 is equal to 5.086 Newton per mm square. Therefore, maximum shear stress at the junction, that is tau is equal to. We are calculating the maximum shear stress at this junction. So this is the formula. P is the shear force, 2.35 into 10 to the power of 6, 1200 into 900, that is the area of this one, 1200 into 900. Y bar is 1265.9 minus 450. So centroidal distance of this section with respect to the centroidal axis of a whole section from here to here, it is 1265.9. So the centroidal axis of this flange with respect to the centroidal axis of whole section will be 1265.9 minus 900 by 2. So that is what it is written here, 450 divided by I into B. So B is width of flange, therefore tau is equal to 1.125 Newton per millimeter square. So principal tension at this junction is equal to, this is the formula, substituting the values what we have calculated, and Fn2 is equal to minus 0.238 Newton per mm square. So this is the principal tension developed in the junction. Now let us calculate the shear stress at the same junction. So in this case what we have done is, in this formula for the value of B we have considered the width of flange. We have considered the width of flange as B to calculate the shear stress. Now in the second case we shall consider this width, that is width of the web, as B and calculate the shear stress. So tau is equal to 2.35 into 10 to the power of 6. Formula is same, everything will be same except the value of B changes. So there it was 1200 and here it will be 600. Here we are going to consider width of the web as B. So everything is same, only this will changes. So when B is equal to 600, tau is equal to 2.25 Newton per mm square. Therefore, principal tension at the junction. So in previous case, we have calculated the principal tension at the junction by considering the value of B as 1200 mm. Here, let us calculate principal tension at the junction by considering the value of P as 600 mm. So Fn2 is equal to, the formula is the same, substituting the values of the formula. So 5.086 is Fx by 2 minus 1 by 2 square root of Fx square plus 4 into tau v square. Therefore, principal tension at the junction is equal to minus 0.83 Newton per mm square. So this is the principal tension developed at the centroidal axis, and this are the, this and this is the principal tension developed at the flange portion.